We grow up learning a very intuitive set of rules about how the physical world reacts to force. Punch a pool of water, and it splashes out of the way. Punch a block of concrete, and you'll shatter your hand. There is a rebellious class of materials that ignores this logic. If you punch them, they behave like solid rock, but if you squeeze them gently, they melt through your fingers like a liquid. This glass laboratory apparatus represents the classical study of fluid dynamics, which began with Sir Isaac Newton and the concept of viscosity, a material's internal resistance to flow. It measures the amount of friction that occurs when the molecules of a liquid move past one another. You interact with the endpoints of this scale every day. Water has a very low viscosity, so it flows quickly and easily. Honey has a high viscosity, so it oozes and resists movement. This diagram shows a thermometer scale directly linked to a flowing liquid, illustrating Newton's primary variable, temperature. Heating up a fluid causes the molecules to move faster, lowering the viscosity. And importantly, hitting or punching that fluid does absolutely nothing to change its internal resistance. Non-Newtonian fluids respond to a different set of instructions. While temperature still exerts an influence, the defining trait of these materials is how their internal resistance shifts in direct response to mechanical stress. By linking viscosity to pressure rather than just heat, these fluids allow a single substance to cycle through different phases of matter on demand. The first category of this anomaly is known as shear thickening. For these specific fluids, like Oobleck, a simple mix of cornstarch and water, applying physical force actively increases their viscosity, making them thicker and more resistant the harder you hit them. Microscopically, this is hydroclustering. During slow movement, liquid acts as a lubricant, allowing suspended particles to drift past each other. A violent force squeezes the liquid out. The particles lock into a rigid, impassable grid, behaving like a solid. Material science companies and the military are actively harnessing this exact microscopic phenomenon to design better defense equipment. This photograph shows early 20th century soldiers in heavy, dented metal chest plates. For centuries, rigid armor stopped fire, but was cumbersome and severely restricted movement. The modern solution is to impregnate lightweight, high-strength fabrics, like Kevlar, with shear thickening fluids. This creates a composite material commonly referred to as liquid armor. This macro footage demonstrates the physics of a strike on this fabric. During a normal combat patrol, the liquid armor bends and flexes easily with the wearer's body. But the millisecond a bullet hits, hydroclustering takes over. The fluid instantly turns into an impenetrable, blunt force dispersing shell at the exact point of impact. By weaponizing a microscopic traffic jam, engineers have designed a material that possesses the protective rigidity of a solid exactly when it's needed, and the lightweight flexibility of a liquid the rest of the time. Mechanical stress doesn't always make things harden. The exact opposite reaction occurs in our second category, shear thinning, also known as pseudoplastic materials. Here, the variable of violent force actually decreases the fluid's viscosity. This photo highlights an everyday frustration, the ketchup problem. Left perfectly still in a bottle, ketchup acts as a solid plug that refuses to pour. Microscopically, this is polymer alignment. At rest, ketchup is a chaotic, tangled web of long molecular chains that blocks all flow. By applying shear stress, the polymers instantly untangle, align perfectly parallel, and slide past one another as a liquid. This phenomenon is why shear thinning allows house paint to glide easily off a moving brush. But in this image, once mechanical stress is removed, the paint returns to a high viscosity solid, clinging to the vertical wall without dripping. Look at these boxes of dried human blood plasma being unloaded. Blood is a complex fluid that relies on this exact pseudoplastic property. The high pressure and physical shear created by our pumping hearts thin the blood out, allowing it to move through the narrow passages of the circulatory system. Without the mechanism of shear thinning, paint would slide in puddles to the floor, ketchup would require shattering glass to extract, and human blood would be too thick to pump through our own hearts. Looking at this render of a shattered frozen droplet, we have to reconsider the grade school categories we use to define matter. We learn early on that solids, liquids, and gases exist in rigid, distinct groups. But non-Newtonian fluids prove that the boundary separating a solid from a liquid is not a hard line. It is a reactive spectrum dictated by force, pressure, and microscopic architecture. At the microscopic level, physical reality is a reactive system of force and architecture, shifting its state based on how we interact with it. Reality depends entirely on how hard you hit it.